Today in this lecture, what we are going to do is, you have already seen two-stroke engines, four-stroke engines. You are also now familiar with quite a few let's say keywords which we have defined in the last lectures. So with this background, we are going to see today in this particular lecture how engines are classified. Now you must have seen several different engines as you grew up. You have seen automobile engines, you have seen engines which are used in agriculture, for example, which are connected to a pump, for example, to pump water. You have also seen engines let us say for grass cutting. Small two-stroke engines are usually used for grass cutting operations, for example. So there are several ways and in the last lecture you have also seen large marine engines, for example. So let us try to understand how engines are classified in the different spectrums of the engines which we see in our day-to-day life. Before we go to the classification of internal combustion engines, let us try to classify the thermal engines per se. So thermal engines, as you know, you can have a major classification. The major classification is, for example, you can have internal combustion engines and you can have external combustion engines. Okay. So as you all know, on the left you see this schematic diagram of a typical thermal engine. So the thermal engine operates between a hot source and a cold sink. Now this cold sink is generally the atmosphere, that is wherever the engine is operating, the atmosphere outside is usually the cold sink where the heat has to be dumped. Part of the heat which the engine gets has to be dumped there. And the reasons for this heat dumping are also known to you. You have studied in your thermodynamics course why you cannot convert 100% heat into work, although the reverse is possible. You can convert 100% work into heat, however 100% heat cannot be converted into work, and you have studied the reasons, the second law limitations of why this is not possible. So coming to this diagram, if you see, this is a typical engine. It takes certain amount of heat from the hot source. Now in our case, for internal combustion engines, it will be usually the chemical energy of the fuel. The fuel can be petrol or diesel or gas or LPG or whatever fuel we are going to burn. The energy will be released, the enthalpy of combustion will be released, and this will since the enthalpy is released in a certain volume, the temperature of that particular gas volume goes up, and from that point onwards our engine starts. That means this is the hot source temperature. So this is the temperature of the combustion chamber, for example. We will discuss in another lecture that how what is the maximum temperature which can be reached in a given volume if you know the quantity of fuel and the oxidant which is available. So this particular hot source, the heat is taken by this engine. Now this engine may have several parts as schematically drawn here. There can be the construction of the engine can depend on, so this is the thermodynamic cycle which actually operates. It can be a Stirling engine, it can be an Otto engine, it can be a diesel cycle based engine, it can also be external combustion engines, for example an engine such as a steam engine, for example, where the fuel is burnt outside the engine. So how exactly this energy is obtained, whether it is obtained inside one of the elements of the engine or it is obtained outside somewhere, is what distinguishes the internal combustion engines from the external combustion engines. All engines will produce some work. We need to get positive work out of the system, otherwise what is the fun in running the engine? So essentially we are converting part of this heat at high temperature to mechanical work, and then of course some part of the heat will be rejected, and it will be rejected to the atmosphere, as I was telling you. So an internal combustion engine, so if you look at the engine component itself, the way this energy comes, the way this enthalpy is released, is what differentiates the internal combustion engine from the external combustion engine. So in an internal combustion engine, the engine such as a gasoline or diesel or LPG or CNG engine, in which the fuel is burnt inside the engine. So as we have seen in the past lectures also, there is a combustion chamber, and in case of a petrol engine there is a mixture of air and petrol which is let us say compressed, and then there is a spark which occurs inside the engine itself. That means the control volume where the combustion takes place is actually part of the engine system, and it directly the expanding gases, they transfer their work, the enthalpy, to the piston which is moving downwards. So that is a very special characteristics of an internal combustion engine, and they are typically designed to operate on any fuel that vaporizes easily or any flammable gas, for example. So if you have, let us say, petrol which can be easily vaporized, for example, diesel also eventually it vaporizes, it is not as easy as petrol, but you have to make a spray with a very large surface area, and you have to surround it with a lot of air which is in turbulent condition, and because of that the turbulent mixing of the droplets of the diesel which is being injected inside the cylinder, it happens with the turbulent air which is around it. And as I told you in the last lectures, this particular let us say diesel engine is always operated with excess air, because we want to ensure that complete combustion takes place inside the cylinder. So after the spray occurs, the temperature is already high enough, and several of these small droplets, they will evaporate, and eventually the auto ignition will start. That means the diesel fuel particles with the evaporated diesel fuel particles will eventually catch fire, and there will be multiple locations from which combustion will take place, unlike in a petrol engine. So this is internal combustion. In an external combustion engine like a steam engine, as I was telling you, the fuel is actually burnt outside the engine. The fuel is burnt to produce heat to make steam, for example, in a steam engine, and then fuel burning can take place within a few meters of the engine, or it can also be several meters away. So the location of the boiler where the steam is generated, for example, can be quite a few meters or quite a few distance away from the actual turbine or the actual expanding device from where the enthalpy of the steam is used to rotate a particular shaft to get positive work out. So that is a major let us say classification. Now coming to IC engines, let us quickly revise again the different parts of an IC engine, for example, so that we can then understand the classification. So the idea is that irrespective of the class of the engine, it can be for example several different classes which we will study, the components, the typical components of an engine actually are the same. However, the way these components are, let us say, integrated together, and the way they are designed and the way they operate will differ from different classes of engines, from one engine to the other. So if you see a block diagram of cut section of a typical engine, you will see several parts which I have listed here. Okay, so let us start with the intake valve. So this is the intake port. From the intake port, this is connected to the atmospheric air, for example, through usually a filter. Okay, so there the air will go in, and you can see the inlet valve, and there is a camshaft. Now in this case the camshaft is located in the cylinder head itself. So where this camshaft is located, in earlier videos or in earlier let us say photographs, you have seen this camshaft can also be at the side somewhere here, and there is a timing gear which is connected. This camshaft is also connected to a timing gear which you cannot see in this cross section. However, this camshaft is on the cylinder head itself, unlike in other big engines, for example, where the camshaft can be somewhere here, but in that case you require a push rod and a rocker arm. The rocker arm is still here, but the rocker arm is directly connected to the camshaft. There is no separate push rod which you can see in this particular engine. So you see there is the intake valve, the rocker arm, and the spring, the retaining spring. This is there for the inlet valve as well as for the exhaust valve. Incidentally, this is a petrol engine. You can see a spark plug. The K is a spark plug here. The B is the valve cover. So there is a cover here, because this cover essentially there is a rapid motion of this rocker arm and the camshaft continuously as the engine is running. So therefore you need to lubricate this entire space, and typically there is a lot of lubrication oil splashing around in this area, and when we study the lubricating system at that time, I will explain you how this lube oil is brought into this system. There is a cover on the top. C is the intake valve. D is the cylinder head, as I told you. So this is the top of the head, the cylinder head, for example. Okay, and then E is the coolant. You can see there is a coolant flow. These yellow portions are the coolant. They cool the cylinder liner. They also cool on the top near the cylinder head. They need to cool especially the exhaust valve here, also the inlet valve, because if the inlet condition becomes very hot, then the density of the air which is coming in actually reduces, and that let us say thwarts the amount of air which can be inducted inside the cylinder in a given stroke. So therefore you need to cool this area, you need to cool the exhaust valve, because hot expansion gases are going out from this particular port from here. So you need to send cooling water around this in the cylinder head also, as I was explaining you in the earlier lectures. Then F is the engine block, the block of the engine at the bottom. The G is the oil pan, all the lubricating oil which is going to the guzzon pin, to the connecting rod, bearing, the top bearing, the bottom bearing, and the crankshaft. This is usually, there is a sump at the bottom where all this oil is coming, which is the H, oil sump. Okay. I, of course, as I told you, is the camshaft. J is the exhaust valve and the rocker arm for the exhaust valve. K is the spark plug because this is a petrol engine. L is the exhaust port. That means when the exhaust valve opens, the gases will go out of this particular port from here. M is the piston. It is well known, we have seen this construction in the earlier lectures also. The N is the connecting rod, and O is the bearing or the bearing which are here, and P is the crankshaft which is rotating. So this is essentially the construction, and as I was telling you, irrespective of the classification of the engine, majority of the construction will be similar to what you are seeing here. Of course, in a diesel engine there will be no spark plug, for example, and then this engine, for example, has to do 4 distinct let us say processes: the intake process, the compression process, the combustion process, and the exhaust process. And in between, of course, when the compression has occurred of the fresh charge which has been inducted from this port here, a spark has to start this initiation because this is a petrol engine. And you can clearly see here the combustion chamber, and the design of this combustion chamber will also affect the way the heat is released. For example, the flame propagates inside this combustion chamber, the way let us say the combustion products are formed, and the dynamic transport processes which occur, the amount of turbulence which is created inside this combustion chamber, the amount of swirl motion which is created inside this chamber. So the velocity field which is generated inside this combustion chamber is actually dependent on the geometry, and therefore this also is an important parameter, as we will see as we go along. You can also see piston rings, for example, and the flywheel at the crankshaft. So several things can be seen in this diagram. So I thought I will repeat this again so that you understand the construction of the engine. And as I was telling you, even though the basic parts are the same, design differences can change the way engines operate and how they are maintained. So the maintenance of the engine is also will depend. For example, if you have a rocker arm, push arm mechanism, then if there are 12 cylinders and every cylinder has 2 exhaust let us say valves and let us say 2 inlet valves, so then every cylinder has 4 valves actually. So you require 4 rocker arms, you require 4 push rods, for example, if it is a push rod type of a design. So the maintenance of the engine also depends on the way it is constructed, and there are several advantages and disadvantages of different construction designs which are available in the market, and therefore we need to understand how these engines are constructed. Essentially they will undertake the same thermodynamic process. However, the way the nitty-gritty at which it will do it on a smaller level, it will actually depend on the way it is constructed. Every design has some pros and cons and caters to the specific need where the engine is applied for power generation. And engine design and structure affects the transport phenomena such as the charge motion, such as the combustion dynamics, emissions, the heat transfer, etc., which in turn affects the engine efficiency. So as we go along, we will actually study how these different types of designs, what is the need of a particular design, what is the purpose a specific design, let us say, is catering to, and things like that. So if you see the classification of IC engines in particular, then internal combustion engines can be classified in several different ways. For example, I am not saying that this is an exhaustive list, but at least it will give you a flavor of how you can classify your engines. So for the first is application. For example, engines used in automobiles are somewhat different than they are used in trucks, for example, or buses or large lorries or transport let us say units. Engine locomotives for railway locomotives, for example, has certain features which are typical to a railway application. Light aircrafts, the design is circular in nature. For example, in olden days, during the world wars, for example, most of the airplanes, there were no jet engines, they were propeller driven engines. Even today there are propeller driven small engines which use an IC engine essentially to run the propeller. So their design is somewhat different. Marine engines, you have seen in the last lectures how marine engines operate, for example. Then portable power generation systems power generation, large power generators, for example, mobile, there can be mobile units or there can be stationary units. So this depends on the application. Then the basic engine design, as I have already told you, there are two types, reciprocating engines and rotary engines. One of the examples of rotary engines which I gave you was a Wankel engine, which you have already seen in one of the earlier videos. Most of the engines are reciprocating, and we have discussed the reasons for this particular design choice. Then there are working cycles. We have also done this, 2-stroke cycles and 4-stroke cycles, for example, which I have explained in detail. The type of breathing, now how the engine breathes, that means how the engine takes in the fresh charge or air and how does it exhale, will also you can classify. So for example, there can be naturally aspirated engines which are admitting atmospheric charge, that means there is no extra pressure, they just as the piston goes down, the pressure inside the chamber goes slightly smaller than the atmosphere, and atmosphere air is automatically sucked in the way we breathe, let us say naturally. When I expand my lungs like this, air goes in because I am reducing the pressure inside my lungs, and atmospheric air enters through my nose inside the lungs. In a similar manner, you can design an engine which is naturally aspiring. However, as you can understand, if you can pressurize the air, if you induct the air at slightly higher pressure, that means the density of that air will be larger, and because the density will be larger, per unit volume you will have more oxidant, that is more oxygen will be available for you to burn, and therefore if you require larger power, that means if you want to burn more and more fuel and you want to do it completely, correctly and more efficiently, then you require if the air is denser, then you can accommodate more fuel, for example, per unit volume of the cylinder, and therefore typically you have seen supercharged engines or let us say turbocharged engines. The difference between these two is that in a supercharged engine, the admitting pre-compressed fresh charge, so the fresh charge is already pre-compressed by some other compressor, okay, by doing some additional work of course, but then you get more work because you have a denser air and you can burn more fuel. So these are supercharged engines. In a turbocharged engines, you have seen several vehicles which are written turbo, for example. So the turbo models in the turbocharged engines, they admit fresh charge which is compressed in a compressor which is driven by the exhaust gas. So essentially what in a turbocharged engine, what is happening, as you expel the air out from the combustion chamber, there is still sufficient enthalpy. You are rejecting the heat to the atmosphere, but the temperature of the exhaust is still pretty high, and you can indeed extract that enthalpy and run for example a compressor, and with that you can give compressed air. So we will discuss in another lecture the construction of the turbocharged and the supercharged engines, and there we will give more details. The valve or port design, for example, there are several ways you can see how the valves are located. I will give you in another lecture several photographs so that you can appreciate what is an overhead engine, what is an I head engine, what is an underhead engine, what is an L head engine, or what is rotary valve systems, or what are the different scavenging methods. Another new word, scavenging, that means how do you push out the exhaust gas. Typically in a 2-stroke engine, the intake air actually helps you to push the exhaust out, because you have only 2 strokes to complete the 4 thermodynamic processes. So there is always an overlap between the suction or the intake of the next cycle with the exhaust of the previous cycle. So you take the help of the incoming fresh air to push the exhaust out, and that typically happens in a 2-stroke engine. So we will discuss scavenging in a separate lecture. So that is another way of classifying the engines. Then how do you prepare the mixture? For example, carburation, fuel injection into the intake port of the manifold, or fuel is directly injected into the engine cylinder. So depending on how the fresh charge is taken inside, you can have different let us say mechanisms by which you can create, let us say the mixture can be prepared. In a petrol engine, it is typically done by carburation. In modern engines, there is also fuel injection of petrol, and of course diesel engines typically always have fuel injectors inside the engine. Then there are several other classifications, for example method of ignition, spark assisted ignition for example in a petrol engine, or let us say compression ignition in a diesel engine, which we have already seen. The type of ignition system, for example in a petrol engine, you can have a battery to ignite, or you can take use of a magneto. That means you create high voltage generation in a small magnetic coil, and this magnetic coil generates high voltage which can be supplied to the spark plug for let us say there are several advantages and disadvantages of battery against magneto and vice versa. Then the combustion chamber design, for example, open chamber, it can be an open chamber design, a disc design, a wedge shape, a hemisphere or bowl in piston. So I will in subsequent lectures I will explain you all these types of different combustion chamber designs. Okay. You can also have divided chambers, for example, you can do the combustion in two different small chambers, one is an auxiliary chamber, one is a main chamber. So the combustion starts from one chamber and then spreads into the other chamber. Why exactly that is done, why it is needed, what are the advantages, what are the disadvantages, we will discuss it in the later lectures. Then the method of load control, for example, if the power is changing, how do you control the load? You can throttle the air fuel mixture, that means you are only allowing less air fuel mixture or more air fuel mixture to go inside, so that you can control the power available at in the working stroke. So the composition does not change, the air fuel mixture composition primarily remains the same, you are just throttling the amount of fresh charge which goes inside the engine. So this is one way of doing it. Of course, then you can also control the fuel flow alone, that means you can just the amount of air remains constant, typically in a diesel engine that is the situation, and then only the fuel, that is the diesel, the amount of diesel is what you actually let us say control, or you can also do a combination of these two methods. The cooling methodology in small engines, for example a motorcycle engine, you have seen that they are air cooled, okay, but the larger engines are all water cooled. So you can have water cooled engines with some antifreeze let us say material added to it, so that they can the water does not freeze in minus temperatures, in negative temperatures, for example. You can have air cooled system. Very small engines can be completely uncooled, that means essentially you only use natural convection or radiation to get them cooled. And then the firing order. The firing order is the order in which the cylinders deliver the power strokes. The strokes are divided along the crankshaft so that a well distributed and balanced firing pattern results, minimizing the strain on the crankshaft. So essentially if you have 4-cylinder engine, let us say, all the 4 cylinders are not giving power at the same time. So the pistons are actually placed in a phased manner, so that if one piston is delivering power, the other piston is actually let us say compressing, the other piston is just about doing the exhaust, and the fourth one is the ignition is starting, for example. So in this manner there is a phase, there is a firing order, that means which engine will fire first, after that which engine will fire, which cylinder will fire the next, which cylinder will fire the next. There is a specific order, and we will discuss that in the coming classes. So in this lecture what we have essentially done is we have tried to classify the IC engines into different types of ways, depending on the fuel, depending on the construction, depending on the combustion chamber design, depending on the method of load control and the cooling water, for example, the applications, for example. And I strongly recommend that when you look around for engines around you, you try to see and try to mentally let us say try to categorize them into certain type of classification which you have studied in today's lecture.